Okay, so again, we are going to practice and learn about adding and subtracting rational expressions for our lesson 7.2 today. This is our warm-up for today's lesson. So just dealing with fractions that only contain numbers for that first example. And anytime you're adding or subtracting fractions, what do we need to find? A least common denominator. Can utilize what method in finding this? The cake method. So we look at our two denominators. We have 10 and 15, and we ask ourselves, are these two numbers relatively prime? They are not, because we can pull out a factor of 5 between each of these two numbers. And when we do, 5 times 2 gives you 10. 5 times 3 gives you 15. We can draw our next layer of cake. We ask ourselves that same exact question. Are 2 and 3 relatively prime? But in this case, they are. So our cake is complete. We take the product of our boot, which is 5 times 2 times 3, which ends up giving us a least common denominator of 30. Now that we have our LCD of 30, we want to manipulate these two fractions to have a denominator of 30. So we multiply each fraction by our fancy forms of 1. 10 times 3 gives you 30. So we have 7 times 3 gives you 21. And then with our second fraction, 15 times 2 gives you 30. So then we have 8 times 2, which gives you 16. Now we simply add the numerators. 21 plus 16 gives you 37. And so our final result is 37 over 30 in improper fraction form. If we wanted to convert this to a mixed fraction, we ask ourselves, okay, well, 30 goes into 37 one time, and then we have this remainder 7, keeping that denominator of 30, and we're done. Now, the second warm-up problem, we're dealing with subtracting fractions, and we have a nice variable in that first fraction, but same thing applies. Our objective is to find that least common denominator between 4 and 9, and lucky for us, 4 and 9 are relatively prime. So cake method really isn't needed. You just take the product of 4 and 9 to get you your least common denominator. And now that we have our LCD, we once again multiply by our fancy forms of 1 to create those equivalent fractions. That first fraction we multiply by 9 over 9. The second we multiply by 4 over 4. So our new numerators are 27x and then a minus 32. And that's it. Because 27x and negative 32 are not like terms. So this is our simplified form. And we're done. Any questions at all from our warm-up? Okay. So let's proceed. So we are on our first objective point, which is being able to add and subtract rational expressions with a common denominator. Maybe I'll have a student read this first paragraph for me. Emmanuel, do you think you can read this for me?
To add rational expressions, we must have a common denominator. When the denominators are the same, you add the numerators and place the sum over the common denominator.
Beautiful. Thank you. And that's exactly what we practiced on the previous page. We want to make sure that those denominators are exactly the same. And then once they are, we just add the numerators and we're good to go. This is just sort of a formalized way to say it in math notation, whether we're adding or whether we're subtracting fractions from one another. So now looking at our first example involving some more complicated expressions, we have the following. 11x plus 28 plus x squared, and this is all over the same denominator, which is our x plus 4. So lucky us, we don't have to do anything to the denominator. We can just rewrite it as is. And then the numerators, we have 11x plus 28 plus x squared. Now, we can simplify that numerator a little bit more, and it might be a good idea to write that numerator in descending order. So starting with that highest degree first. And then I think you'll realize you'll be able to factor that numerator into what two binomials? What are factor pairs of 28 that add to 11? And then Alex. 4 and 7, right? So we can break up that numerator into an x plus 4 and an x plus 7. Why is it important to do that? Well, what do you notice about that denominator? They have that common binomial. X plus 4 divided by an x plus 4, this just cancels out. So in simplified form, we're just looking at x plus 7. And we're done. Let's take a look at example 2. We once again have this same denominator. So right now, let's just rewrite that denominator and not do anything to it. At least not yet. And then as for the numerator, we'll just write it straight across. Maybe we'll be able to combine some like terms. Because we're subtracting, you don't want to forget to distribute that negative to each term in that second fraction. And that's why I really wrote those parentheses there, because you're subtracting the entire fraction, not just that first term. So we have a minus 4x squared, a minus x, and then a negative times a negative is a positive, so we have that plus 9. And now I'm just going to highlight some like terms that we'll be able to easily combine. And so the blues, when we combine these like terms, what do we end up getting? What's 5x squared minus 4x squared? X squared, or 1x squared, right? What about what's negative 7x minus x? A negative 8x. And then what's a 3 plus a 9? That's 12. All right, we're almost there. Now we can look at factoring out that numerator and factoring out that denominator. So numerator, factor pairs of 12 that add to -8. -6 and -2. So x minus 6, x minus 2 is our new numerator. What about our denominator? Factor pairs of -18 that add to -3. -6 and +3. So we have an x minus 6 and we have an x plus 3. Do any binomials cancel out in the numerator and the denominator? Yeah, our x minus 6's. So our simplified form ends up just being x minus 2 all divided by x plus 3. And we are done. Any questions on this example? We will continue to trek along to our second objective for today, which is finding the least common denominator of rational expressions. So it's just finding your LCD that involves variables. And maybe I'll have a student read this. Mia, do you think you can read this for me? Numerical. Good. Awesome. So once again, utilize your cake method. Just focus on the coefficients first, aka the numbers in front of the variables first, and then deal with the variables in order to get your LCDs. And then this is just a step-by-step procedure in finding your least common denominator of rational expressions. I just personally think the most concrete and straightforward way is to utilize your cake method that we've been practicing over the past few months now. So now let's apply it to this example 3. Notice how now our denominators are different from one another. We have an x squared minus 2x minus 3, and then we have an x squared plus 4x plus 3. So when you are looking for a least common denominator, it's in your best interest to just factor these out first, because there might be a binomial that they both share. And if they don't, then at least you know that, and then you can just multiply all of the binomials together to get your LCD. So in that first example, when we factor out our denominator, what do we end up getting? What are factor pairs of -3 that add to -2? -3 is a prime number, right? So only factor pairs 1 and 3. And with the use of negatives, we have +1, -3. So we're looking at x plus 1, x minus 3. And then let's go ahead and look at that second fraction. Factor pairs of 3. Once again, 3 is prime, but this time adds to 4. They're both positive, so we're just looking at +1, +3. 1 plus 3 is 4. So our binomial is x plus 1, x plus 3. And would you look at that? What binomial is shared between the two? that x plus 1, right? And so because they share that x plus 1, we don't have to repeat that twice. Our least common denominator, we just write that x plus 1 one time, and then you want to include both of, sorry about that, both of the other binomials. So your x minus 3 and your x plus 3. This is how you find least common denominators dealing with rational expressions. In this question, they didn't ask you to add or subtract these two fractions. They just simply asked you to find your LCD. In later examples, we'll add in the adding and subtracting. But does everyone see how that works? Factor it first, look for commonalities, and then every binomial that's different, you sort of take the product of to find your least common denominator. And then finally, we're on our third objective before we jump into some nice examples where we'll be adding and subtracting rational expressions with unlike denominators. So it's just putting everything together at this point. We now know how to find least common denominators of rational expressions. So we're going to be utilizing that skill. And then the last step is finding those equivalent fractions with that least common denominator, and then adding and simplifying the numerator and simplifying the fraction overall if you're able to. So in general math terms, we're looking at a fraction a over c, and we're adding b over c to that. That c is after we've found that least common denominator and multiplied these by our fancy forms of 1 to get those equivalent fractions. And then that very last step is adding just the numerators up and then fully simplifying. So now let's tackle example 4 together. Again, our first step is being able to identify that least common denominator. And lucky for us, we don't really have to do any factoring here since we're looking at two binomials. So if one's x minus 3 and the other's x minus 2, what do you think the LCD is? Just the product of the two of them, right? Since they're both different from one another. So we have x minus 3, x minus 2. This is our LCD. We're not looking at, good question, Angel. We're not looking at conjugates quite yet. Conjugates come into play when we're dealing with square roots in the denominator. So we're just looking at finding that LCD. So we're keeping those operations exactly the same. And then what we're going to do is we now want to manipulate, and I'll draw these as two separate fractions at first. But we want to find what our equivalent fractions are with that new denominator of x minus 3, x minus 2. We want to multiply by that fancy form of 1. So that first fraction is being multiplied by what? Well, it has green, but it needs yellow. So we're multiplying it by x minus 2 over x minus 2. Whereas that second fraction, what are we multiplying this by? Yeah, exactly. It has yellow, but now it needs green. And so now the denominator for that first fraction is a green and yellow, and the denominator for that second fraction is also green and yellow. Now let's utilize our distributive property. distributing that 3 to each term. We have 3 times x, which is 3x, and 3 times -2 is a -6. And then we're going to utilize distributive property for that second fraction. We have 2 times x, which is 2x, and 2 times -3 is -6. Denominators are exactly the same now, so we can just combine those numerators together. And so we're looking at 3x minus 6 plus 2x minus 6. And we're not quite done because we can combine some like terms in that numerator. 3x and 2x ends up being what? Good. And a -6 minus 6 gives us, good. So we have 5x minus 12 in our numerator. And then our denominator, we have our x minus 3 and our x minus 2. Now, can this be simplified anymore? It can't, right? Because 5x minus 12, there is no common factor between those two terms, and those aren't like terms. So that's our fully simplified result. Questions, comments? How do you guys feel? Scale of 1 to 5. 5 being like, I got this. 1 being, I don't understand life. All right. Let's do another example together. So again, anytime you tackle examples like this, really look at your denominators. That's the first thing your eyes want to draw to. And then you also want to ask yourself, are they in fully factored form? Now that second fraction is, right? We have the 2 over x plus 1 squared. If you wanted to write x plus 1 squared as x plus 1 in parentheses, x plus 1, you can. That's easier on the eyes. But that second or that first fraction is our difference of squares, which can be factored into what? I think I heard it. X plus 1, x minus 1. Good. Now that they're both in factored form, it's quite straightforward with identifying what our least common denominator is. Do they share any commonalities? They share an x plus 1. So we don't have to repeat that. We just have to write that one time. But then the other ones, they don't share. So we need to write both of these. And so we have our LCD. And now we want to put it into our equivalent fractions. Multiply by our fancy forms of 1. So that first fraction is being multiplied by what? Which one is it missing? It's missing an extra x plus 1. X plus 1 times 1 just gives you x plus 1 for that numerator. And then what about the second fraction? What is the second fraction? It's denominator missing. Yeah, it's missing that x minus 1. And so you just want to be mindful. We have this minus here. So -2 times that x minus 1. Now we can all put it under one fraction because our denominators are exactly the same. You just don't want to forget to really utilize that distributive property for that second fraction. So we're looking at x plus 1 minus 2x minus 2 times a minus 1 gives you a plus 2. Good. We're not done quite yet because we can combine some like terms in our numerator. Great. We have x minus 2x gives you a negative 1x. And then we have a 1 plus 2 gives us 3. So we have negative 1x plus 3, which cannot be simplified anymore. So this is officially our final result. And we're done. You could have also written the numerator as 3 minus x, and you would have received full credit. Getting the hang of it a little bit more. Yeah. Let's do another example together. Again, first step, draw your eyes to the denominators. They're in expanded form, so let's see if we can factor those out so that we can easily identify what our least common denominator is. That first fraction, the denominator can be factored into what? X minus 3x plus, good. That second fraction's denominator can be x, very similar to last example, right? X plus 3, or not last example, 2 examples ago, and x plus, good. Let's write the numerators back in. Do they share any common binomials? Good. So let's not repeat that with our LCD. We'll just write that one time. And then the others, we have our x minus 3 and we have our x plus 3. We need to add in both of those. Now that we have our LCD, we can put this all under one fraction. So now that we're getting much better with this, I'm just gonna put it all under one fraction now. Save yourself a step. Yeah, good. So that first one we're multiplying by that fancy form of 1, x plus 3 over x plus 3. And that second one we're multiplying by x minus 3 over x minus 3. So our new numerator, use your distributive property. We have x times 8, which is just 8x. And I always like to go from the term on the outside to inside the parentheses. And then 8 times 3 gives you that plus 24. This is a positive, so we don't have to worry about it being a negative and distributing that negative. And we have a plus 3x squared minus 9x. We're not done quite yet because we can combine some like terms. we have that 3x squared isn't combined with anyone. And then we have an 8x minus 9x, which gives us what? Negative 1x. And then that 24 also is all alone. And then can we factor that numerator? Can utilize our AC method, right? So um if it stays like this, you might only get partial credit because you always want to put it into simplified form. And you might, when you factor that numerator, you might be able to cross out a binomial in the numerator and the denominator. So when we utilize our AC method, we're looking at factor pairs of 20, 40, 60, 72 that add to -1, which is what? A -9 and a +8. So now let's rewrite this 3x squared to be 3x squared minus 9x plus 8x plus 24. Pull out a GCF. We're going to pull out 3x from that first term. So we're looking at x minus 3. And then that second term, we're going to go ahead and pull out an 8. So we're looking at x plus 3. Did I do something wrong? I did. -9 times 8 doesn't give you +72. So are there any other factors where you can take the product to get 72, but then it adds to -1? I actually don't think there is. We have 24 and 3, 36, 2, 18, 4. Yeah, there aren't any others. So, Gabriella, in your case then, because this numerator is a prime trinomial, you can indeed leave it like this. And you'll get full credit. Does everyone see that? Yeah. All right. So I might have a student read this paragraph for me. Let's see. Kelly, do you think you can read this for me? All right. So now let's look at example 7 together. And you'll notice in example 7, we now have 3 fractions. Again, ask yourself, are these denominators all in fully factored form? And the first 2 are, so we can just rewrite as is. But the second one, we can pull out a GCF. What can we pull out? a u, and then we're left with u minus 1. Now we can go ahead and easily identify what our least common denominator is. What do you think it is? You know that these two share u minus 1, so you don't have to repeat that twice. You can just write the u minus 1 once. And then you also know that these two share a u, so you don't have to write the u's twice. You can just write the u's once. And that's it. That's your LCD. You can also rewrite it if you want to have that u in front. So it's u in parentheses, u minus 1. Either or works. But now we want to put all of these three fractions into equivalent fractions by multiplying by that fancy form of 1 and getting that denominator to be u in parentheses, u minus 1. So in that first fraction, what are we multiplying the top and bottom by? U over u, right? That second fraction, what are we multiplying the top and bottom by? It's got this. Good. And then that third fraction, are we multiplying by anything? No, it's already in least common denominator form. So now let's use our knowledge of distributive property. We have a 2u squared, and then this is a plus, so don't have to worry about distributing negatives. U minus 1 times 1 is just u minus 1. So plus u minus 1. And then we have this minus 2u minus 1, so we do need to distribute that negative to each term. So we have a minus 2u and then a plus 1. This is a very common mistake that people make when you're subtracting and you're dealing with that binomial. Even though there aren't visual parentheses, you still need to distribute that negative. And now let's combine some like terms. 2u squared has no like terms, but u minus 2u does. And so does that negative 1 plus 1, which actually just ends up canceling out for us. That really works in our favor. And so what are we left with? 2u squared, yep, minus u. But can this be simplified more? Can you pull out a greatest common factor in our numerator? You can pull out a u. And when you do, you're left with 2u minus 1. All over u in parentheses, u minus 1. What can you pull from the numerator and denominator? U divided by u is just 1, so our final simplified result is just 2u minus 1 all over u minus 1. You cannot cross out the u minus 1s in this last bit. That does not work, and that's because this is 2u minus 1. 2u minus 1 is very different than u minus 1. Questions at all? And the last bit is just now putting it into rational function format. Same exact techniques. It's just now you're dealing with it from a function perspective. So you're given these two functions and we're just simply asked, what is the difference between f of x and g of x. What's f of x minus g of x? So all we're doing is our f of x is x plus 5 all over x minus 2 minus, and then our g of x is our 5x plus 18 all over x squared minus 4, which can be factored into what two binomials? We have some difference of squares here. Yeah, our x plus 2, x minus 2. Good. And then, same procedure as before, identify that LCD. They both share that x minus 2, so we just have to write that once. And then we have an x plus 2. Put it all under one fraction. X minus 2, x plus 2. Multiply by your fancy forms of 1, that first fraction, x plus 2 over x plus 2, good. That second fraction, do we have to multiply it by anything? We do not. Utilize your FOIL properties, first, outer, inner, last. So we have an x squared plus 5x plus 2x plus 10, and then distribute that negative to each term in that second fraction, minus 5x minus 18. Combine like terms. X squared is all alone. What's 5x plus 2x? 7x minus 5x is just 2x, right? The 5x's just cancel out, and we're left with a plus 2x. And then what's a plus 10 minus 18? Yeah, negative 8. This is all over your x minus 2x plus 2. Factor out the numerator. X plus 4, x minus 2. Do any binomials cancel out in the denominator? The x minus 2's cancel out. So what's our final simplified result? Well done. Questions at all? Now, where do you guys stand on a scale of 1 to 5? Again, 5 being like crushing it, 1 being like, I still have no idea. Okay, cool. Again, I would say if you're in the 2 range, please try to get in that additional hour of tutoring besides that 1 mandatory hour. And so these are just additional workbook exercise problems to further enhance your knowledge for both section 7.1, which you guys did asynchronously on Friday, as well as today, our 7.2. This is just adding, subtracting, multiplying, and dividing our rational expressions. That was the last example of 7.2. In terms of 7.3, which will be your asynchronous lesson for this Friday, you're gonna be learning how to simplify complex rational expressions. So you know what complex fractions are. We're at this point in the curriculum where it's just, we're now looking at more complex versions of what we've already learned together earlier in the course. I am going to stop recording now.